only share to 25 people. So if you can't get access, you should be able to see what I'm streaming now on YouTube, just in case. Okay, I'll take the big me away, and let's move that over here, and let's get started. So reminder, this is being recorded. You can interact fine with the text. In fact, that's something I forgot to do. I need to start up the Discord on my phone, and I will be looking at the CET466 discussions channel, just so that I can see it there. So let's just put that somewhere where I can see it. There we go. Okay. Yeah, it's actually over there, so sometimes I don't see it. Let's have a look. So we've done the initial introduction and a quick review of flip-flops. Just a reminder that Lab 1 is due this evening. If you haven't had a chance to go through Lab 1, please try and do it. I will have some time later in this morning's session to answer any questions about either Lab 1 or Lab 2. But that'll be later on in the session. If you do want to ask questions, feel free to use the voice channel, either voice or text. Just note that I may not see the text channel as quickly as I hear the voice. So this is where we are this week, and I want to talk a little bit about synchronous counters and clock generating circuits. So I hope you understand the difference between the words synchronous and asynchronous. They're being used a lot at the moment because of the whole way teaching is being done differently. What we're doing right now is what I would call a synchronous delivery course, right? We're all online at the same time, and you're watching the slides and listening to me talk about them. Asynchronous lecture delivery is where I record a video some time earlier, and then everybody watches the video whenever it suits them, and then maybe you get together a little later and answer questions about it. But and that's the asynchronous delivery. Here, in logic design, the synchronous piece means that there's a fundamental clock signal, right? An oscillating clock signal. It's going between 0 and 1 at a specified rate, at a constant rate, and that's driving what's happening in the rest of the circuit. You can have asynchronous digital circuits, and we'll talk a little bit about that, particularly with JK flip-flops. They have a synchronous aspect and an asynchronous aspect. Asynchronous means that the effect on an input change to the digital circuit happens immediately. There's no waiting for a clock transition. A synchronous circuit will have the outputs won't change until there's either a positive transition on the input clock or a negative transition on the input clock, depending on how you do it, depending on the sort of device you have. Okay, so last time we talked about these different types of flip-flops. That is the logic device, not the footwear. There's a D flip-flop or a D latch. There's slightly different things, but I've just put it up for D latch. There's a T or toggle flip-flop. There's an SR or set reset flip-flop. And there's a JK flip-flop, and that's not a joke. RRR. So what we didn't do last time is we didn't really think about how the flip-flops work in terms of their inputs, and so I thought we should go through that in a little bit more detail. So here's an SR flip-flop. I'm not drawing the individualized gates in this case. And it's got three inputs. It's got an S, an R, and a clock, CLK input. And it's got two outputs. It's got a Q and a Q bar, right? And the idea is that Q and Q bar should be complements of each other. If Q is a 1, then Q bar is a 0, and vice versa. One thing you need to be clear about is on this clock input, there is no bubble, right? There's no dot on the yellow or beige coloured box. If there were a dot there, then that would be a complementary input or an active low input. Because there's not, it's a standard input, so it's an active high input. And what that means from a clock perspective is that the flip-flop triggers on a positive going transition. So when the clock signal goes from a 0 to a 1, things happen in the flip-flop. And the way you show things happening is in the table on the right hand side over here, right? You've got if you've got 0 and 0 on the inputs and there's a positive clock transition, then there is no change on the output. If you've got set at 1 and reset at 0, then and there's a positive clock transition, then the output gets set to 1. 0 and 1 in the transition, the output gets set to 0. It's not clear what happens if you've got both S and R set to 1 and there's a positive transition. It could be just about anything could happen. It could be a 0, it could be a 1. We don't know. So one of the things you've got to be clear about when you have an SR, when you use an SR flip-flop, is that when that clock transitions, you can't have both S and R being 1, because you'll have ambiguous settings. Excuse me while I take a slug of coffee. So the other thing to note is all three of these inputs, the clock, which I talked about before, but also the S and the R, are active high. That's why set is high, does the set, and reset is high, does the reset. Okay? Everybody okay with that? Well, there's another one on the next slide. And here's the same thing, except now we've got a bubble on the clock input, right? So that means it's an active low input. And what that means for a clock is that the device triggers on the negative edge. So when the clock input goes from a 1 to a 0. And other than that, the transition table is exactly the same, right? The only difference between this one and the previous one, right, is that now the clock transition is going down rather than going up. Oh, I forgot some of these slides have transitions on them. I really dislike transitions on slides. Oh well. Okay, so the only difference here is we've got this bubble on the clock input. Okay, so here's a JK flip-flop. And the nice thing about a JK flip-flop is there's no undefined behavior. Right? If you look in the table on the right-hand side there, the previously undefined behavior that we had with 1-1 means that now the JK flip-flop toggles the output. Right? So if the output had been a 1 before the positive going clock transition, now the output's going to be a 0, and vice versa. And again, this one has all non-inverting inputs. And here's a timing diagram showing the clock and indicating that the positive going transitions are when we're interested. And here's the output Q, and here's the different values of J and K, right? So the output starts at a 1, and that at the first transition, positive going transition, K is 1 and J is 0. So K is 1 and J is 0. So that means the output is forced 0. Okay, so it's the reset. The next one, we've got a 1 and a 1, so it's doing a toggle. Then we've got a 0 and a 0, so there's no change. Then we've got a 1 for J and a 0 for K, so that's a set operation. And then the next two, both J and K are 1, so we toggle. So this one, it's exactly the same, except now we've got that bubble again on the clock. So now the transition is going to happen on the negative going transition of the clock input. So there's no difference between this table and the previous one, except that that clock column is on the negative going transitions. Okay, here's a D flip-flop, and the D flip-flop, one way to think about it is it's a delay, right? So the input on D gets transferred to the output on Q on the clock transition. Again, this one has both D and the clock input are non-inverting, there's no bubbles on them. So when the clock transitions, the whatever was on the input at D gets transferred to the output at Q. Okay, so here the output rather was 1, and then our first transition, D is 0, so it gets set back down to 0. And the next one, D is 1, so the next transition goes to 1. It's 0, it's 1, it's still 1, now it's 0 again. Okay, so what you can see here is it's possible for the D input to not be synchronized with the clock, but the Q output effectively has to be, right? So these transitions should all line up. Now, remember we talked about propagation delay or rise and fall times. Even though I've drawn it happening at exactly the same time, it's not necessary that it is precisely the same time because of those rise and fall times we talked about last time. Right, so the edge triggered D flip flop is one that transitions on that. In this case, there's no bubble on the D input, or on the clock input rather, so it transitions on the positive clock transition. But if that edge detector is not used, then it's a slightly different operation. It's called a D-latch. Right. And this is the way a D-latch is shown. So rather than having a clock input, it's got an enable input. Right. So if the enable, in this case it's a non-inverting input, if the enable is 0, then nothing changes on the output. And remember, when you see an X in the in a logic table, or in a truth table, or in a transition table, you should remember that X means don't care. X means that D can be a 1 or a 0, and it's the same operation for both of them. Right, so here we've got there's no change. If the enable is a 1, then 0 on the input becomes 0 on the output, or a 1 on the input becomes 1 on the output. Okay. Don't know why that transitioned so quickly. So one thing I said before is about asynchronous inputs. For a JK flip-flop, the J input and the K input are synchronous, right? Changing the input on J and K only has effect, in this case, on the negative going transition of the clock, right? There's a bubble on the clock input, so it only has effect on the negative going transition. There are often two other inputs on a JK flip-flop, the clear and the preset, right? And these are related to the J and K inputs, but their effects happen regardless of what's happening with the clock, and regardless of what's happening with the J and K inputs. Right, so in the diagram on the right hand side, you'll see, in the table on the right hand side, you'll see that the top half of the table is exactly the same as what we had before for the standard synchronous operation of the JK flip-flop. But the table at the bottom, now what you'll see is we've got values of preset and clear being 0. Either one of them is 0 or both of them is 0, right? And really that first line in the second half of the table, that first line is the same as this one, right? It's just saying, well, I don't know. I don't know whether I agree with having that line in there, right? Because just because preset and clear are 1. Oh, that's the other thing. I'm calling these preset and clear, but notice that they do have bubbles on them, and that's why there's a bar across it. So this input for preset is active low, which is why there's a bar across the top, and this one is active low as well. So the operation of clear only happens when the clear input is 0, and the operation of preset only happens when the preset input is 0. You'll notice again we've got an invalid result. This is very similar to the SR 0 and 0, or 1 and 1, I think it was a non-inverting version. So you want to try and make sure that that never happens if you are using the asynchronous inputs. Oops. So the two really interesting pieces is that when clear is 0 and preset is 1, that is clear bar and preset bar, then we have an asynchronous clear, and if it's vice versa, if preset bar is 0 and clear bar is 1, then we have an asynchronous set. Right? So it changes the output of Q to a 1. Right, so we've got I think that's, oops. When you're thinking about flip-flops, in fact logic circuits generally, you need to have various timing considerations taken into account. You need to make sure that the clock pulse high or low times are long enough for the effect to happen. Sometimes if the clock goes high really quickly and then changes back to low really quickly, like really quickly, then the effect won't be felt. Similarly, you need to have asynchronous pulses have an appropriate width, and then you need to have the transition times being fast enough. You don't want them to be floating between 0 and 1 for too long. And I think you will have used TTL devices in CET466. But you probably haven't used CMOS devices. Let me just move that over here. And make it bigger. Because I want to ask a question. Right, so the question is, what does TTL stand for? And Kyle, do you have any ideas? I think Kyle's on the channel. Kyle Bechtold. You should be able to see the tag. Okay, Justin, what did you tell us? Typing or voice is fine, whichever works. Aha! No! You've done too much networking. TTL in TTL does stand for time to live, or time to in networking, but in this course it stands for something else. This is acronym overload, I'm afraid. Okay, let me try someone else on the bingo call. So I think is that Abraham? Is that right? I've forgotten. Let me just get up the class list. Yeah, it's Abraham. So Abraham, do you have any idea what TTL stands for? Okay, we'll try somebody else. And I'm afraid.
Is it time to live?
No, if you check the of Justin's answer, that's basically what Justin said in the chat there. And
That
I
was my first thought.
well, and I accused Justin of having done too much networking, because certainly TTL stands for time to live, or time to live in networking. Okay, Anthony, you go. Let us know. Yeah, transistor logic, right? So let me just get in here, and TTL equals transistor logic, right? With the I might just make that a capital L so we can see what it is. And eek, I didn't want to do that. Right? So the technology used to implement TTL gates and the 7.4 series of devices, the 7400 or the 74LS00, and all of those other TTL devices, all of those other 7.4 series devices, are all implemented via TTL. And they're the reason that it's called TTL is because they used to the technology before TTL was called resistor transistor logic. Right? And as you can imagine, just thinking about Ohm's law and the power dissipated, P equals VI, and Ohm's law, V equals IR. If you're using the RTL logic, meant that sometimes there was always current flowing through a resistor, and that meant they tended to be a bit more power hungry, and tended to heat up a bit more. And I think the 5.4 series of devices were RTL devices. I can't quite. They were actually a little bit before my time. So even when I was an undergraduate, we were using TTL. And so TTL, because they use, sorry, I just got my alarm clock going on for some reason. Because they don't use resistors as part of the logic circuit, they don't dissipate as much power. Okay. So let's go with see what CMOS means, and I'll try the bingo draw again. Ah, Justin, you're up again. You've already had a go, so I'll try somebody else. So, David, is that? You got an idea what CMOS stands for?
Metal oxide something.
Yeah, that's right. That's right. It stands for complementary metal oxide, and I think it might be silicon, right? I believe that's true. I'm going to Google it because my brain is just like all of yours at the moment. Oh, it's semiconductor. Okay, so the S is semiconductor. Usually the semiconductor is silicon, but it's not necessary. In fact, it probably, so there's the C. M. Now, why don't we use the CMOS devices in the lab? Any ideas? And I'll go with the. Let's see if I can get the bingo to select someone else. I'm sorry, I'm not sure who Afaf is. Is that? I really should get a match between people's Discord names and your actual names. That's okay. Okay, no response there, so let's try again. So Stephen, do you have a suggestion as to why we don't use CMOS much in the labs? And voice or typing is fine, like I said. Either is good. Because it's slow? CMOS can actually be pretty quick. That's not the reason I'm looking for. No clue? That's okay. So the reason why is because CMOS devices tend to be more susceptible to static electricity damage than TTL devices, right? So you know the way we work in the lab, where we have plastic buckets of devices, right? And you, I'm not sure how Professor Zanella does it, but I usually bring the plastic buckets of devices up to the front of the class, and then get people to come up to the front of the class to get the individual gates, and then you put the individual gates into your hand, right, and you walk back to your lab space. Unfortunately, your hand and that act of walking, now I don't know whether the lab has probably had some anti-static measures taken, so it's probably not as bad as this, but simply touching the leads, the legs on those devices can induce static damage. So that's why you'll find well, MOSFET is a particular type of transistor, and those types of transistors are often implemented using CMOS technology. Okay. MOSFET stands for metal oxide semiconductor field effect transistor. Right, it's a type of transistor. So what we'd find if we used CMOS devices in the lab, and you were touching the pins on those CMOS devices, is we'd blow them up without, you don't have to actually zap, cause a spark, a noticeable spark, in order to damage them. And what you'll find is when you are handling CMOS devices, they usually come in conductive foam, so the pins are stuck into conductive foam, and then you don't want to, when you're moving them from the storage in conductive foam to the actual device where they're going to sit, you don't want to touch the pins. You need to use tweezers or some other tool, IC extraction or insertion tool, in order to move them around. Okay, so that was kind of fun. And again, they're perfectly good chips. It's just when you're working with them, you've got to be careful to make sure that they don't get zapped. Okay, let's try. Do we have another page here somewhere? There we go. Right, and this is just some of the timing considerations, right? So when you've got a clock just because I draw clocks and all the other logic numbers with abrupt transitions doesn't mean that that's the way they actually happen, right? These signals are running in the real world, so they can't go abruptly, right? Even if you've got the best system possible, there's still going to be a little bit of capacitance or a little bit of inductance hanging around. So, right, you get I equals C dV dt. So if you have a completely abrupt change in voltage, dV dt, the derivative of the voltage, is going to be very big, so you're going to get a current spike. So what that means in real life is that instead of the clock abruptly transitioning, it transitions something more like this. And as a result, you get a slight delay in what happens on the output, right? And then the output also takes a little bit of time to transition because it also has a bit of either stray capacitance or stray inductance, and so it's going to have the same sort of shape. But then there's a time between that 50% on the clock input and the 50% on the Q output, and in this case it's TPL, the time for propagation from low to high, and then the delay going the other way as well, going from high to low. And yeah, this is just showing that it works with the synchronous clock, but you also have to take it into account with the asynchronous. The asynchronous inputs have the same shape. So one of the things we're going to come across later in the course is this issue of glitches or timing problems. Right? If you've got a lot of flip-flops in a circuit, and we're going to talk about counting circuits soon, and those counting circuits tend to have several flip-flops. If all of those flip-flops are connected to the same clock or triggered of the same clock, and the output of one flip-flop gets connected to the output of another, then you can have a potential timing problem because of propagation delays. Okay. Right, and then it's just talking about edge-triggered flip-flops rather than their timing. and this is just, right, so you've got to assume that the hold time requirement, the hold time is how long you need to keep the inputs stable in order for the flip-flop to actually take notice of the change on the input. And the flip-flop output will go to a state determined by logic levels present at its synchronous control inputs just prior to the active clock transition. Right. So that's an assumption we're making. It may not be true, but it can help. Right, so here's an example. We've got two JK flip-flops, and you can see they're both being driven by the same clock. The JK flip-flops have an active low clock input, and we've got a 1 and a 1. We've got a 1 and a 1 on the input of flip-flop 1, and the K input of flip-flop 2 is grounded, so that's a 0, and the J input of flip-flop 2 is coming from the Q output of flip-flop 1. Right, so here's our initial state. Q1 was in state 1, Q2 was in state 0, and we have a negative going transition because we've got an inverting clock input. So here we get the clock pulse, and here's a little bit of transition delay from high to low. CMOS can operate at lower voltages, but again, these timing issues happen with all of them. I don't believe they're explicitly have more timing problems. So the question in the chat that the video can't see is that Anthony's asking, is that also a reason we wouldn't use CMOS because they operate at lower voltages, creating more timing problems? Like I said, I don't believe that's the case, but let me take a note, and I will follow up with some more information about the difference between CMOS and TTL. Good question. Okay. So what's this saying? Q2 will respond properly to the level present at Q1 prior to NGT of clock, provided Q2's hold time requirement is less than Q1's propagation delay. Now, let's see if we can unpack what that means. Let's just, that's a bit better. So Q2 will respond properly to the level present at Q1 prior to NGT of clock. What does NGT mean? Let's see. Okay, NGT. Let's make a text box. NGT. Any guesses?
That give transition?
Yeah, there we go. Negative going transition. Exactly. Okay, and then the other obvious one, and my wife has just made a banoffee, so that's what that message is. So sorry about that. Yeah, so PGT is positive going transition. And I really should set my it's yummy. I'm just going to turn on my do not disturb wherever it got to. There it is. So hopefully yes, so complete aside, the reason for the Pi is during the I was without power for 6 days during the storm, and friends of ours were kind enough to donate their generator to us for a few days. So we promised, I gave them a bottle of wine when I picked up the generator, and we promised when when we were back up and running that we'd buy. They like pies. Who doesn't? I mean, let's face it. But we promised that we'd give them some pies. So there's a banoffee and a Bakewell tart going to them later today. So yes, they're yummy. Sorry about that. I know it's okay. So let's go back here. So Q2 will properly respond to the level present at Q1. So we want to have the whatever value is Q1 is going out to Q2 prior to the level present at Q1, prior to the negative going transition of the clock. So there's a negative going transition of the clock, and there's Q1. Provided Q2's hold time requirement, TH, is less than Q1's propagation delay. Right? So provided the input is okay, is seeing the value here, in enough time, is sees the value faster than any transition coming through here, through the first flip-flop, right? In this case, this is going to toggle, but provided that toggle propagation is longer than the hold time, that is it's the look time, it's the time that says, okay, I've got my I'm told I have to transition. Oh, what value is it? And it's that delay between being told it has to transition and looking at the value that it's going to use. And provided that time, the look time here, is longer than the propagation delay from input to output, then we're all good. Does that make sense? I hope I'm that's what this slide is talking about. Let me just pull that up here. Okay, so here's another picture, and here we've got 3 flip-flops, and they're connected together as a counter, or sometimes you call it a frequency divider. So let's just, right, there are 3 flip-flops, so it's one way to think about a flip-flop is as a 1-bit memory device, right? So when we've got 3 flip-flops, that's a 3-bit memory device. So let's just, actually before I make it go big, so each flip-flop divides the input frequency by 2. So we can see here that all of the J and K inputs on all 3 flip-flops are set to 1. That means the flip-flops are set to toggle mode, right? They're going to just change the value of the output from 1 to a 0 or a 0 to a 1. The output frequency is 1/8 of the input frequency. A 4th flip-flop would make the frequency of 1/16. So let's just see what that's saying. Right, so here is our clock input, right? And this is sort of back to front. This is flip-flop 0, flip-flop 1, flip-flop 2. And we're not using any of the pre-bar or clear bar inputs because they're all tied high. So we're only interested in synchronous operation. So here's our clock and our all of our devices, but the clock is only going into the first one. The clock, it's an inverting input, so things only change on the negative going transitions. So if initially Q was 1, and that is actually a negative going transition as well, then the toggle operation makes it go 0, 1, 0, 1, 0, 1. So you can see immediately that for 2 clock pulses, there's 1 Q out, Q naught pulse, right? So that going from that clock to Q out is a division by 2, right? The frequency has gone from, say it started out as 100 Hertz, the frequency is now 50 Hertz, right? And then let's just move that out of the way. Then you can see the output of Q naught is going into the clock of Q1, and so now Q1 is going to do the same thing, but it's going to operate on the negative going transition of Q naught. So the interesting pieces here, let me see if I can draw a shape. Right, the interesting transitions for Q1 are on the negative going transitions. Let me see if I can make a, don't know whether I want it there, right? So, and let's see if we can make the there we go, right? So the interesting thing for Q1 is other negative going transitions on Q naught. So these are the interesting pieces here. And you can see again the difference between Q1 and Q naught and Q1 is a factor of 2. So the difference between the original clock and Q1 is now a factor of 4. And then similarly for Q2, the interesting transitions are the negative going transitions of Q1, right? And the difference in frequency between the Q1 output and the Q2 output is a factor of 2. Difference in frequency between the Q2 and the Q naught is a factor of 4. The difference between the Q2 and the original clock is a factor of 8. Right? That's why it's called a modulo 8 counter, because it's effectively counting up to 8 and then going back again. Right? So 0, here we've got the values of Q2, Q1 and Q0, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, etc. And then it transitions back again here. Okay? So it's about time to call the roll. I'm just I don't use attendance in any way. I do like to keep track of who's on the call, so I just hit the call roll. Okay. So we've been going for about an hour. Let me just have a quick look at what's happening on the where's the view gone? There it is. So we're on page, what page are we on? 519 rather, we're down here. So let's just see where we are here. And that's just a blow up of the one we just did. And it's just saying, so this should be a subscript, right? It's base 2. And base 2. And this should be base 10. I hope everybody remembers their base 2 and their base 10. Should know base 10. Base 2 is a little tricky. And that's just right, so let's just have a look at this one. There we go. Probably shouldn't have made them quite so small. Okay, so another way to draw this out is like this state transition diagram over here, right? Here we've got Q2, Q1 and Q0, 0, 0, 0, and that transitions to 0, 0, 1, which transitions to 0, 1, 0, and then we'll go all the way around again. Right, so each of these arrows is what's happening with that clock transition. Right, and here's just the same thing, but in a table. And really what's happening with this table is this end of the table gets connected back up to the top end of the table, right? Because you can see this is just going to be the same, start filling in the same thing again as the start of the table had, right? It's just it's a different pulse number, right? We start off with pulse 1, 2, 3, 4, 5, 6, 7, 8, etc. Okay. Okay, so what I'm going to suggest is we have a brief break. When we come back, let me just pull it up on the screen. When we come back, I'm going to talk about I'm going to introduce this problem, and then I'm going to talk about, I'm actually going to hop around in the slides. I wanted to talk about something else before I talked about generating clocks. But I'm going to talk a little bit about this problem, and then I'll talk about different ways of thinking about devices and about the stateful devices, and then we'll try and finish this problem. Okay, we'll try and do it together. But let's have a 5-minute break first up. Let me just put up a 5-minute counter.
Are we practicing this in multisim, just like on a paper?
We're not going to do this one in multisim just yet. I don't want to. I just want to do it on paper or, electrons first. I don't want to do it in multisim. But yeah, the question is to try and figure out how to do this this sort of a problem. So the example we just went through, that was a modulo 8 counter, and it goes from 000 to 001 to 010, etc. This one is doing something a bit different, and it's not counting exactly the way we would expect. So I just want to try that. So I'm just going to take like I said, a 5-minute break, and we'll put that up. And when we come back, does that answer the question? Yeah. When we come back, no worries. When we come back, I'll talk about that. We can try and do that. Okay. So I'm just going to go turn my webcam off briefly. There we go. And I'll be back. Okay, just about ready. It looks like there's about a 30-second delay between what I'm seeing and what's happening on YouTube, so that could be a bit problematic. Okay. So I believe, let me just check that I did do it. I believe I uploaded this to the materials channel. There it is. Right, so you should have access to this PDF. So what's happening, let me just explain what's happening. Let me just bring that up. Can't hear anything? Okay, maybe I... where's it gone? There it is. Sorry about that. Let's try that again. Thank you. So my problem is I looked at, I was listening, I could hear myself on the YouTube stream, but I had muted the stream here on Discord, so that's why you couldn't hear me, but I could hear myself. Anyway, sorry about that. Too many buttons to press. I actually I really have gained a much greater appreciation of the people who do audio engineering and video engineering and all the behind the scenes things that people do to make YouTube channels. I've learned a bit, but my production values are nowhere near as high as a lot of people's, and I really have gained a much deeper appreciation of the level of effort that goes into what a lot of those people do. So it's impressive. Anyway, so what's happening here is we've got a present state and a next state, right? So our present state goes 0, 0, 0, goes to 0, 0, 1, same as before in the counter that we had. Sorry, I've got... yeah, sort of. It's not really a green screen. It's a green tablecloth. But anyway, I really should splurge and get a real screen. Okay, so you can see there are, in each state, whether it's present state or next state, there are three flip-flop. There are 3 bits, right? And the first question, and I just gave away the answer anyway, is asking how many flip-flops are needed. Well, the answer is 3, right? I said in the earlier part of the lecture that one way to think about a flip-flop is as a 1-bit memory device. Well, there's 3 bits in each of these states, and that means that we need 1 flip-flop per bit, so that means we need 3 flip-flops. So let's move on to the let me do this. I'm going to insert the printout if I can figure out where the printout is. There it is. Let's make it a bit bigger so we can read it. Okay, so ooh, I don't seem to have added everybody to this. Anyway, I should figure out how to make this a class OneNote notebook. But anyway, so let me do this. So we had this first one, right? How many flip-flops? We had, I said that a flip-flop is like a 1-bit memory. So that means that there are 3 bits of state. Right, so that means we need 3 flip-flops, at least. So the next question, what sort of flip-flops can be used? I'll try with the bingo again. So I think that's Javier. Do you have a suggestion about what sort of flip-flops we could use? Given, remember, there's D, T, SR, and JK.
This is JK.
JK only, you think?
You could probably also use an SR.
Yeah, I reckon you could probably use either an SR or a JK. JK is probably preferable. The only reason it's probably preferable is because of that SR problem of the ambiguous, I'm trying to say the wrong word, ambiguous output with both S and R inputs high, and JK is much better behaved. So in general, so why wouldn't you use, let me try somebody else, why wouldn't you use a D or a T flip-flop? I don't know who Jazzy is.
Not sure.
Not sure? Okay, that's okay. Let's see if somebody else. I'll go with the bingo again. Zach, any suggestions as to why you wouldn't use a D or a T flip-flop? Okay, so let's just try up here, right? So JK, that's probably preferable. Because they're better behaved. Apart from though when the asynchronous inputs are used, they don't have any ambiguous outputs. SR could also probably be used, but we need to make sure we avoid the S equals 1, R equals 1 case. Yeah, not compatible, but there's sort of perhaps a deeper reason, right? Or not a deeper reason, but a more specific reason, right? For a T flip-flop, all a T flip-flop does is toggle the output, right? it does nothing else. So unless your state machine just toggles each bit based on the clock, that one's not really going to be doable. I think you could probably get away with a D flip-flop. The only problem with a D flip-flop is I suspect the logic might be more complicated. Because remember, what a D flip-flop does is it just delays the connection between the input and the output. That means you need to make sure you know precisely, you form the input appropriately based on what the output is. So my only concern with this is that maybe the logic is more complicated. Maybe. I think it's possible, but right, so JK, we can do that. SR, okay, and D possible, and I'll just do a little twiddle rather than an actual check mark. Okay, so the next question is, what's the excitation table? So let's have a look at excitation table, and I'm just going to Google it. Excitation table, and I'm going to say we're going to use JK flip-flops. Right, and this is a little different from what we had before. And let me just take a screenshot of that, and that way I can paste it into here. Insert picture, and we'll go from the screenshots directory. Oh, there it goes. And I don't know whether I can make that a bit bigger. Let's do that and see if we can make it a bit bigger. There we go, so you can read it. And I probably didn't want to do that. Okay, so this is the excitation table. And what this shows us is if you want the output of a JK flip-flop to go from 0 to 0, then what you need to set the inputs to are 0, and we don't care what K is. If we want to transition from 0 to 1, we want a 1 on J, and we don't care what K is. If we want to transition from 1 to 0, we want a we don't care what J is, and we want a 1 on K. And if we want to transition from 1 to 1, we don't care what J is, and K should be 0. Okay, so that's the excitation table, and that excitation table page on Wikipedia has the other flip-flops as well. Let me just bring that up again. Right, so There's a T flip-flop. Right, tells you what to do. There's the SR. There's the D flip-flop. Right, they all have excitation tables. Let me just put that into the links. Okay. So now it says draw the K-maps for the required logic. What does that mean? Any ideas? So, I'm just going to have to look at something quickly. Apologize for this. What I want to try and do now is do something I haven't done before. So be wary. Right, so what I'm going to do is I'm going to try and send everybody into breakout rooms. Right? So what'll happen is you'll disappear from the classroom and you'll end up in a chat with a few other students. That'll be called breakout. And I want you to discuss in those groups how you go from the information we have so far to that next line, draw the K-maps for the required logic. So let me just see if this works. I haven't tried it before. So there should be 6 breakout rooms. So I don't know how many students that means, probably 3 or 4 per breakout. So let's see. Okay, it's being a little slow, but I think Donica and Nasmeen, you're in one, so have a chat.
Yep.
And the others are gradually populating. Okay.
Okay.
Like, I don't know what the fuck's going on here, really. I'm trying my best.
Good. That's good. I'm glad. So have a think, have a chat. I'll leave you alone. I'm hoping that everybody ends up in separate breakout rooms. But anyway.
Gang's all here.
Apparently, I don't know, this doesn't seem to have worked quite the way I expected, so that's all right.
I see multiple breakout spaces, but this like everyone's
Yeah,
either
but
in the first one or the last one.
yeah, there's something wrong there. I think I may have an old version of Professor Broderick's breakout code, so maybe I need to fix that. Okay, so this doesn't seem to have worked quite the way. You can see all the breakout rooms, and but what was supposed to happen is it was supposed to divide you amongst them relatively evenly. But
It looks like you have to leave yourself.
oh really?
It looks like you're by yourself. Yeah, that's what it looks like.
Okay.
I will. I'll separate myself.
Okay, so yeah, if you can maybe form groups of 4 or 5 in the different breakouts, that would be good.
I think.
Why? This is
Hey.
always happening.
Okay, so keep in this group and see if you can figure out what to do next. Okay, so keep in this group and see if you can talk to each other and figure out what to do next. This looks like a 498 group mostly, except for Eddie. Hi Yasmin. Yeah, I don't know if you want to. Maybe you could join one of the other groups, and I don't know why it didn't distribute people appropriately. But anyway, I thought I'd try it out.
Okay.
So if you could join one of the other breakouts and see if we can get an answer. Okay.
Alright.
But there's three PowerPoints.
No, so there should be a. Oh, he did post it. Okay.
I mean, just the assignment, not the like.
Okay, there's discussion going on in the other rooms. There's nothing happening here. Does anybody have any? At least not since I joined. So.
Yeah, not much.
No. Okay.
Just me.
Yeah. Oh well. So the aim is to try and figure out what the next step is. So what we're trying to design a circuit that does this sort of counting, right? And the key piece is to go up here. Let's get a different color. Maybe get that one. Maybe get let's orange is good. And oops, I need to draw. So this is the present state. Let's call it Q2. This is the present state for Q1. This
You're
is.
not streaming.
I'm not streaming. Okay. That.
Yeah, there's no.
Right. So if you look at the table, let me see. Oh, can I stream here? I can stream here separately. Let's try that. That one. Okay. So can you see that now? Yeah.
Yes.
Right. So the present state we've got Q2, Q1, and this is Q0, and then this is the next state, and again this is Q2 for the next state, Q1 for the next state, and Q0 for the next state. So what we want to do is we want to figure out what our inputs are to generate this list of outputs. Right, so let's think about it. Right, so let's just pull out Q2, right? And we've got 0, 0, 0, 0, 1, 1, 1, 1. That's the previous or the present state. And then the next state is the next state is 0, 0. Looks like it might be a problem. 1, 1, 1, 1, 0, 0. Let me just see what that problem is in the other. Okay. Okay. Let me pull everybody back from the rooms and let me go through this with everybody. Sorry about this. I should have practiced it with before trying it out. So let me remember how to get it back. I think it's call back. It's just call back. So let me do that. And we should all appear back in the main room, I hope. So
Did you see what he gave us? I don't see anything that he gave us.
So
Like,
I just called everybody back. So hopefully you should transfer automatically. But in case you don't, I just thought I'd let you know. Okay. Hi.
Javi's back.
I've just called everybody back to the classroom. I'm hoping it's going to transfer,
Okay.
but we'll see. Okay.
cool.
Hi, Zach. I called everybody back to
Yep.
the. Yep. You should go automatically, but for some reason it's taking a little time. Okay, sorry about that. We'll try that again once I've debugged it. Professor Broderick and I have been playing with the Discord bots, and I don't know whether I've got the latest version. I know Professor Broderick has been working quite well with breakout rooms, but for some reason that didn't work as smoothly as I expected. So the question was, well, there seems to be a big leap from the third bullet point there, what is the excitation table for those flip-flops, to draw the K-maps for the required logic. Okay? And I was just working with one group to try and pull that out. So what I did is I went back up to this table, this transition table, state transition table, and I pulled out the Q2, if you like, the most significant bit series of numbers. And I tried to write that rather messily here, right? And then what I want to do is I want to add it over here, and I'm going to, because this is Q2, I'm going to call this J2 and K2. What inputs do I need on J2 and K2 to get a 0-0 transition? Well, the JK excitation table tells me, right? A 0-0 means I need a 0 and an X. A 0-0 means I need a 0 and an X. A 0-0 means I need a 0 and an X. A 0 to 1 means I need a 1 and an X. And a 0 to 1 means I need a 1 and an X. A 1 to 1 means I need an X and a 0. A 1 to 1 means I need an X and a 0. A 1 to 0 means I need an X and a 1. And a 1 to 0 also means I need an X and a 1. Okay, so what this is now going to tell me is this is I need to design a logic circuit that gives this as my output for J2 with these inputs. Is that right? I'm not, sorry, I'm losing my train of thought. Yeah, that's right. So what we do is we put a we put that line in, right, where we're trying to figure out how to make J2 happen like that, right? So what we do is we form a Carnot map. I don't know if you remember Carnot maps. I should have drawn it a little better. Right? And I'm gonna, yeah, K-maps, right? So Q2 is going to be 0 or 1. Q1 or Q0 is going to be 0, 0, 0, 1, 1, 1, 1, 0. Okay, and I need to, so I actually do need to know Q1 and Q0. So let's just fill those out. So that's 0, 0, 1, 1, 1, 1, 0, 0, and Q0. I wish I could write, it'd be wonderful. You'd be able to read it. Is 0, 1, 1, 0, 0, 1, 1, 0. Okay, so for this first one, we want to look at these three. In fact, let's use a different color. Let's use a blue color. We want to look at these three because they tell us it's this box here on the Carnot map, and the entry for J2 is a 0. Right, so we put that one in there. The next one is 0, 0, 0, 1. So Q2 is 0 and we've got 0, 1. So we put that entry in there. So we've done that one. Then it's 0, 1, 1. So 0, 1, 1 is this box here. And again, it's not lined up, but it's a 0. Right, so this one here goes here. And then the next one is 0, 1, 0. And believe it or not, I probably should have drawn a box to get everything to line up properly. Right, so 0, 1, 0 comes over here, and that entry goes in here, and that's a 1. And then we get 1, 1, 0, so 1, 1 0 is here. And so 1 1 1 1 0 is this bottom right hand box. So this one goes here. We get a 1. And then I've got too many boxes here. I've got too many numbers. Oh, drat. Because those bottom 4, why have I got it? 1, 2, 3, 4, 5, 6, 7, 8. For some reason I've got too many things here. So I think maybe, let's just go back. I apologize. I should have drawn a table and done it properly tabulated so it lined up. Right, so let's just see what's happened. We want to go from 0 to 0, and that's a 0, 0 to 0, that's a 0, 0 to 1, and that's a 1. So that one there shouldn't be there. And that should go to there. That should go to there. Right, and then 1, 2, 3, 4. One, 2, 3, 4, 5, 6, 7, 8, 9. That one, that's wrong. Ah, that's the other problem. Let me start this again. I apologize. This is let me do this. I want a table, and I want a table with 1, 2, 3, 4, 5, 6 columns, right? That's about right. Let's make it 7, and let's make it as long as we can. And let's do that, right? So right, so this is Q2, and let me make it a little larger. That might be a bit more readable. So this is Q1, and this is Q0. This is Q2 next. And okay, so what I'm going to do is I'm just going to take this transition table. So let's see if we can move this table up so I can see both of them at the same time and fill it in, right? So that is 0, 0, 0, and Q next is 0. And then that's 0, 0, 1, Q next is 0, 0, 1, 1, Q next is 0, and then we've got the 1, then we got 0, 0, 1, 0, and Q next is now 1, and then we've got 1, 1, 0, Q next is 1. Oops. Just want to move that up a bit, and I wonder if I can insert another table, insert rows below. Okay, so we just did 1, 1, 0, so now we need to do 1, 1, 1, and that's a 1. And then we need 1, 0, 1, and that's a 1. And then we need 1, where have we got to? There, 1, 0, 0. That should be a 0. And that's a 0. Okay, sorry about this. I should have done it this way to start with. My messy handwriting meant that I got too many lines in there. Does everybody understand what I'm trying to do so far?
I'm a little confused, to be honest, by the Q next.
Okay.
Here.
Okay, so we've got this. This is the state transition table that we're trying to implement, right? And the current value of each of the Q bits, the Q2, Q1, and Q0 are these ones. And what we want to happen is we want, in fact, let me draw it up. Maybe. Yeah, that'll do. So what we're trying to do is we're trying to do a state transition that goes from state 0, 0, 0 to 0, 0, 1. And then we want to go from 0, 0, 1 to 0, 1, 1, right? That's what this line is telling us. And then from 0, 1, 1, we want to go to, excuse me, 0, 1, 0. And then from 0, 1, 0, right, we want to go to 1, 1, 0. And then from 1, 1, 0, we want to go to 1, 1, 1. And from 1, 1, 1, we want to go to 1, 0, 1. And from 1, 0, 1, we want to go to 1, 0, 0. And from 1, 0, 0, we want to go back to 0, 0, 0. Okay, so these are the present state bits, okay? And all I'm doing is I'm just trying to figure out how to I'm decomposing it, so I want to try and figure out how to get Q2 to change. So this is Q2 next here. So these numbers I've put in these first three columns, right? And Q2 next is just this column, because I want to first of all focus on getting Q2 next right. Does that help at all?
Yes.
Yeah? Okay. So what I want to try and do is now find out what J2 and K2, the inputs to my flip-flop that is containing Q2, I want to try and find what the inputs are. Right, so to do that, I need to look at the state transition table up here. So, and the transition, the only transition I'm interested in at the moment is going from Q2 to Q2 next. So 0, 0 means that I have looking up the the excitation table is 0x, and 0, 0 again is also 0x, and 0, 0 again is also 0x. Then it's 0, 1, so now it's 1x. And then the next one is 1, 1, right? Q2 to Q2 next is 1 and is x and a 0. 1, 1 again is x and a 0. 1, 1, 1 is x and a 0. And 1 to 0 is now an x and a 1. Okay, so now I have this. What I'm going to do is I'm going to use that table again, and I'm going to insert a 3 by 5. I think that's all I need. And let's just make it big so we can read it. Okay, so down here is Q2, and across here is Q1 and Q0. Right, so down here we have Q2 is 1 or 0 or 1, and here we have 0, 0, 0, 1, 1, 0, sorry, 1, 1 or 1, 0. So now what we're doing is and I can now maybe draw it, should be okay, maybe, right? So we want to say, so this is J2, this is the J2 table. We want to figure out where this 0 goes in the Carnot map, and Q2, Q1 and Q0 are all zeros, so that's 0, 0, 0, 1. So this one goes in here, and I'll try and do the right, so that's 0. The next one is 0, 0, 0, 1, which is this one, so it goes there to 0. Next one is 0, 1, 1, so it's there. And the next one is 0, 1, 0, which is here, and that's a 1, right? So that last one I just did, where's it gone? There it is. Right, this one here goes into this entry. Okay, and then all the rest of them for Q2 is 1, don't cares. Okay, does everybody remember how to use Carnot maps for logic minimization? I'm gonna...
This is definitely familiar. I just had a question about, do we make 2 separate J2 K-maps for like Q1 and Q1 next, and then Q0 and Q0 next as well?
Yes, except we're going to have to do a K-map for K2, and then a K-map for J1 and JK1, and then a K-map for J0 and K0, right? Because for every input, we need a Carnot map, right? And because where we're heading, right? We said that we had. Let me get back drawing. We said we've got 3 bits, right? So we've got J2, K2, and Q2 bar, and we've got another one to hold Q1, and we've got another one to hold Q0. So we need to find expressions for every one of these inputs in order to get the whole thing to hang together. Right? So this is the J2 Carnot map, and Anthony's saying that you form expressions where there are... Yeah, so what you do with a Carnot map is the aim is to group all of the ones together in as large a group as you can. And they have to be a power of 2. So they have to be a size of either 1 box, which is 2 to the 0, 2 boxes, which is 2 to the 1, 4 boxes, which is 2 to the 2, or if you're really lucky, 8 boxes in this case, which is 2 to the 3. In this case, we're not that lucky. We can just group these two together. Remember, a don't care can be a 1 if we want it to be, right? So what this is saying to me is that the input to J2 has to be Q1, Q0 bar. Right? And the nice thing about flip-flops is that you get the bar version for free, right? So what that means here is on the input to J2, we have an AND gate, and the things we're ANDing together are Q1, and then that is actually Q0 bar and Q0 bar. Okay, so we've done one of the 6. And then now we've got to do the same thing again for K2. And let me just grab a copy of this. Yeah. Right, and I'm going to, actually I'll just leave this one up here. This is the J2 one, and let's just line it up so that we get everything right. And I'm going to use this one for K2. So now for K2, we've got to go through again and the first few of these, the top line for K is all don't cares, right? Then the 110, 110 entry here is a 0. The what's the next one? 111, that's this one, is also a 0. The 101, which is also this one, is also a 0. And then we have a 1 here. Get the right font size. Right, so this is now the this is the K2 map. So this is K2, and we can do circle these out because this circle doesn't care what value we have for Q2. It can be a 0 or a 1. That means Q2 gets simplified out, and all we have now is that K2 is equal to Q1 bar Q0 bar, right? It's in the this is the 0, 0 column for Q1, Q0. So then we can draw up the input here for K2, and we already have a line for Q0 bar. We also need to bring over Q1 bar. Anyway, that's a bad line, but anyway, so I hope you get the idea. Does that start making sense? Is there any?
Yeah, it started making sense.
Yeah.
I think what I was asking, I think I was just asking a little too ahead because I think we'll now it's starting to get make sense.
Okay, so And now we've got to do the same thing again, right? But for J1 and K1, and then for J0 and K0. I'm not gonna do that online. Again, we've gone about an hour, and we've got another couple of hours to go. So I think you and I need a break again. So we'll do that. I'll come when we come back. I'll reprise what we've just done on this tutorial sheet, and like I said, I'll try and make sure that you have this available, because I thought I had it set up as a classroom one, but I haven't, because I should see all your names here if it's a classroom one. So I might try and do that. So let's, unless anybody has any other questions, let's take maybe a 10-minute break while I get some more coffee, and I'll see if I can figure out why this isn't a classroom notebook. And that way, the reason that's good is then you can get access to all of these handwritten notes without me having to do anything. You should just be able to open up OneNote and access the information. Okay, so let's do that, and I'll see you back in about 9.5 minutes. Thank you. Okay, putting all the different versions of mute back on. So this is the book I should have been using. So for some reason I opened up the wrong notebook. Let me see if I can quickly copy that page across to here. There we go. Okay, so now I've got it. And I have a slight problem now because I'm doing some work at Fairfield as well, Fairfield University. I can't quite figure out how to tell Microsoft which of my Microsoft accounts to use, the CCSU one or the Fairfield one. So I've got to do most of my work in incognito mode in the browsers, because otherwise it remembers the last one that I used, and I can't quite figure out how to nuke all the settings to get the to get it to work. Okay, so that's the tutorial, and let me do I wish I could type. And I'm just going to do I want to do that? Let's just go back to the slides. That might be better. Where are we? And I'll go there. So during the break, Javier asked about whether the sheet's going to be uploaded. Not yet. I will probably get you to upload the tutorial sheet. It's not accessible, but I think it'll help you if I can give feedback on what you're doing for this stuff that will be accessible in the future. So let's, I'll after this session, I'll create a Blackboard assignment. It'll be called an assignment, but it's not part of the assessment for the course. The aim is to give you feedback on what you're doing. Okay? Oh, it's not that, Ray, it's not that bad. Come on. So, I just want to skip a little bit ahead. Right. I do want to go back and talk about the timer stuff, but I just want to quickly talk about this first. Right. So when you've got a circuit or a system that needs sequential logic, there's two ways that people think about it. Sorry, I'll just see what that is. Okay, Celine, I'll talk to you later about figuring out that. Where are we? There. And we want to go back to the discussion. Right, there's two ways to think about this, and it's the people who thought about it early were who it's named after, Moore and Mealy, right? And the two components in both cases, one component is the combinational logic, that's the AND gates and OR gates and NOT gates and what have you that is used to make the system. And then the other piece is the memory, right? And you can think about that, and those two pieces are the same in both, right? The combinational logic feeds into the memory, just like we just did with that J2 K2. The memory is the Q1, Q2, Q1, Q0, feeding into combinational logic, which are those single AND gates that we got, and then those single AND gates in the combinational logic of what we were doing feed into the memory, which is the flip-flop. Okay, so they're the two paths. The combinational logic determining what the memory is doing, and then the memory being available to the combinational logic to make that determination. And the same here. Right? And there's a couple of differences between the Moore machine and the Mealy machine. The Moore machine doesn't appear to have any inputs, right? The Mealy machine has inputs. That means we can affect what happens from the outside. The other significant difference is the Moore machine, the outputs are taken directly from the memory, and in the Mealy machine the outputs are formed from the combinational logic. Okay, I think somebody should be on mute. Okay. And the idea here is it depends on exactly what you want, right? One way we could have tackled, we didn't, but let's just go back to this question, right? One way we could have tackled this is to say we're going to we're just going to use a counter, right? And our state is going to be nothing more than a counter that goes from 0 up to 7 back to 0. Because a simple counter like that is very easy to design. We had a picture of one in one of the earlier slides, that 3-bit modulo 8 counter that we talked about. That already did this for us, right? So the thing that doesn't give us doesn't give us this state transition, right? It gives us 0, 0, 0 to 0, 0, 1, but it doesn't give us 0, 0, 1 to 0, 1, 1. If all you're interested in is outputs to say this is the state, right? What you could do is you could say, okay, what I want to have happen, it's the wrong one. Let's try that again. When I'm in 0, 0, 0, that's my state, and I just output 0, 0, 0 directly. When I'm in 0, 0, 1, I output that directly, so that's okay, 0, 0, 1. The next transition though, actually let's try that again, sorry. So where is it? 0, 0, 0, 1, 0, 0 goes to 0, 0, 0. So what we need is the counter, right? So 0, 0, 0, 0, 0, 1, 0, 1, 0, 1, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and then 1, 1, 1 down the bottom. It's a bit overlapped, right? But so what I can do is I can say, okay, I'm only interested in a tag, right? So what I can do is I can form my sequence like this, but then instead of just outputting 0, 0, 0 in this state, I can output something else. Instead of outputting 0, 0, 1 in this state, I can output something else. The same with all of these, right? And that's what's happening. The way we designed the system initially is like this. We just assumed that the outputs we were interested in is what's actually being stored in the memory. But what I'm talking about now is the memory is just doing counting like you would normally count, but we're doing something else in order to form the outputs. Okay? And right, so here's a fixed modulus binary counter, and then the dashed line. So we've got just going from 0 to 1 to 2 to 3 to 4 to 5 all the way up to 25. Once we hit 25, we're going back to 0. Right? And this is one way of dealing with this. It's a modulus 26 counter. 0 to 25 means there are 26 states, and this is a way of dealing with it. So yeah, that's about all I want to say with that one. Right, here's another one. Right, this is the idea with this one is it's a Moore machine. Let me just go back. Right, remember a Moore machine? We're getting outputs directly from memory. Right, so here we've got outputs directly from memory. And my daughter's asking me if I want coffee. Of course I want coffee. And then whereas this one is a Mealy machine, and it's doing things a little differently. Let me just have a look at this one. Have a look at that one. Okay, I'm gonna go back over this next week because I do want to. Let me just go to my slides, and I'm just going to. So I've talked about that. I haven't talked about the clock generating circuit, so I'm going to have to move that off until next week. and I will talk a bit more about the Moore and Mealy machines next week. Let me just quickly have a look through here. Yeah, so this is the simple counter. Actually, this is a. Does anybody know what a grey code is?
Nope.
Yeah, you do? What is it? Or you don't? Who is DK Exos? You're tagged.
That would be me, Anthony.
Oh, it's Anthony. Okay.
Yeah, it changed my nickname on
Yeah.
the server.
Yeah. I need to rewrite the bot so it pulls out the nicknames rather than the IDs. So yeah, go ahead.
Yeah, honestly, I can't remember too much about Grey Code.
Okay, so grey codes are used. Right, grey codes are used. Let me go back to OneNote so I can draw. Right, so grey codes, and let me go to white so it's easier to see, and close that up so we got more room. So let's go with grey code. Grey codes are a special sort of counting. They're not 0, 1, 2, 3, 4, 5, 6. What they are is counting so that each subsequent binary number differs from the previous one by 1 bit. Right? So going from 0, 0, 0 to 0, 0, 1, that's okay. That's part of the grey code. 0, 0, 1. Now we can't go to 0, 1, 0, right? Because now we've got 2 bits that have changed. These 2 bits are...
It would be 0, 1, 1.
Right, so that one can't be it. So to go where you go from 0, 0, 1 would be 0, 1, 1, right? And that's a grey code. Then from 0, 1, 1, well, you could go various places, but one way to go would be to 1, 1, 1. Right, and then from 1, 1, 1, maybe you could go to 1, 1, 0, and from 1, 1, 0, maybe you could go to 1, 0, 0, and from 1, 0, 0, where would you want to go from 1, 0, 0? And we've got 1, 2, 3, 4, 5. I've probably done this in the wrong order because we still need to hit 1, 0, 1.
Quick question, is Grey Code limited to 3 bits?
No, it can be any number of bits, right? If you've got 10 bits, again, the grey code order would just be each subsequent binary number only differs from the previous one by 1 bit.
Okay, thank you.
You're welcome. Okay, and so that's why that slide, and I probably should have looked at the slide before I started counting, right? So you can see that, let me see if I can... Can I draw on this? Maybe I can. Let's go with red. Right, so I can see that the... Ooh, that's cute. I didn't realize I could do that in PowerPoint. Right, you can... It's only differed by 1 bit. Right, here we've got this one changed. Here we've got this one changed. Here we've got this one changed. this one changed, the middle one changed, that one changed, and then that one changed, right? So we only change one bit at a time in a grey code counter. And so for the grey code counter, you could do the same present state, next state thing that we did for the tutorial example. And there's the transition table for the JK flip-flop. And there's an example of how to do it for this grey code counter example. And there's all of the Carnot maps for the 3 bits, right? And you've got various groupings of ones and don't cares that you can do. And in the end, you end up with a circuit like that for a grey code counter. It's got the AND gates feeding into some of the bits, right? But then there was a bit of logic there. Let's go back a slide. Yeah, so this logic here for J0 and K0, you could do that using an AND gate and an OR gate, but it turns out that Q2 bar Q1 or Q2 Q1 bar, that is actually a so this is actual, where's it gone? Yeah, there. So it turns out that Q2 bar Q1 or Q2 Q1 bar is actually simpler to write as Q1 exclusive OR, it's Q1 exclusive OR Q2. Sorry, my writing is atrocious today. I don't know why that is. Right, and that's why there's an exclusive OR gate, or 2 exclusive OR gates for J0 and K0. Right, feeding into J0 and K0, there's Q1 and Q2, and in fact this has got this is an exclusive NOR gate because it's got that bubble on the output, because it looks like one of these is the inverse of the other. Anyway, let's leave sequential design there. Like I said, I will put up an assignment for you to have a go at that tutorial problem that we went through, at least for the first, for J2 and K2. I just have to write it down, otherwise I will forget. I'll give you feedback if you want, but this grey code example is in the notes is a fully worked example of how to go through it. It's a different problem, but it goes through all the details. Okay. A reminder, we have a lab today, and a reminder that lab 1 is due this evening, right? Let me just go through lab 1 maybe. Unfortunately, it's easier for me to run ooh, it didn't open up. Oh, that's going to open up. That's all right then. So I've selected the Engineering Science Technology desktop, and let me just move it over so you can see it. Maybe, I hope. It's preparing Windows. Okay, so I'm only allowed access, or anybody's only allowed access to this for 3 hours at a time. Okay, so what I wanted you to do is the following. This is for lab 1, right? Because I noticed there's still quite a few people who haven't tackled lab 1. I wanted you to go to github.com/kootsup, which is me, and check out the repositories and get the test module. You should be able to download the test module. Yeah, I've just been working with Celine, but she's having exactly the same problem. And my suggestion to her is to try using a different extraction tool rather than using the inbuilt Windows extraction tool. Try something like 7-zip. And let me find the link to 7-zip. I think it's just 7zip.org. Is that right? 7-zip.org. Yeah, so I'll put that in the links direct to the channel. Where have I got to? There we go. So try that. I don't know whether that's going to help. Right, so I've just downloaded it. I'm going to show in folder. And I'm just going to try and extract all here. Yeah, see, for me it works, and I don't know why sometimes. What browsers are you using? That might be maybe there's some different browser. Wade or Celine, can you chime in? What browser? Chrome? Yeah. That's really bizarre. Microsoft Edge? Yeah, so I'm really. This is a Windows machine, and I've done it on my other Windows machine, and it all seems to come down, and I don't know why it would be different. Like I said, my only suggestion is to go to 7zip.org and maybe get the download. I won't be able to install it on this machine. Okay, thanks, Wei. And extract it here. What I'd suggest, because this machine doesn't keep living, right? Or your data on it will get wiped away. What I'd suggest is once you've downloaded it, copy that download over to your OneDrive. You should be able. It's the equivalent of your old M drive, right? My old M drive contents are here, and I suggest you copy it over to there. And I'm just going to make a new folder, and it's just going to be work, right? And I'm going to paste that there. Okay, so then what I wanted you to do for the there it is. For the first lab was to fire up Quartus Prime Lite. You should be able to install this on your own computer if you have a Windows computer. But if you don't, then you should be able to just use this Citrix server to get access to a machine with Quartus on. That's why I'm doing it, rather than my machine that I'm talking to you on now is a Mac, and they don't have a version of Quartus Prime that runs on a Mac. I tried to get it to run on a virtual machine inside the Mac, but there's all sorts of issues with that, so I stopped. Now when you first try and open up that file, it won't automatically show you the project file. So you need to change the file type and go to project files, and then you'll see the VGA piece, and that should open up now, right? And what I want you to do is I want you to hit the build button to make sure that you can build using Quartus Prime. And what should happen is these progress bars should fill up and get a green tick, and eventually you should be able to see all green ticks down here. Okay, and that's what I want you to. I did notice some people uploaded screenshots that didn't have all green ticks in here, and if you wondered why I gave you 80% instead of 100%, that's why. So feel free to. I think I've set up the lab to allow 3 submissions, and that's what I normally do for all of my homework or assignments. So if you feel like you want to get that 100%, feel free to try it again and get those green ticks in the image, and I'll regrade it if you upload it before 11:59 p.m. tonight. So that's one thing I needed you to do. The other thing I needed you to do is to run multisim somewhere. This is multisim 14.2. Somebody had multisim 14.1. I provided it's version 14. I don't think it makes a big amount of difference for me. We're only going to be using multisim for a couple of things. Once we there's a half adder and full adder lab that I want you to do, and you probably should use it for your big project at the end, but I probably won't use it other than those 3 instances. So the thing that you needed to do for the first lab was to take a screenshot of this showing that you've got it started up, and a screenshot of this showing the greens, and that's it. Upload those 2 screenshots. Okay. We have a slightly different lab today. Let me just go to labs. Oops. I might have to make that smaller, and I'm just going to put that away for now. I might come back to it later. Right, so here's our lab 1. So here's the lab that I want you to do today, and I basically want you to in multisim implement a half adder, and what I want you to do is take a video of the circuit being exercised showing the 4 different inputs, right? There's 4 different inputs here, 0, 0, 1, 0, 0, 1, 1, 1, and I want you to show that those inputs generate the right outputs in multisim. Does everybody remember what multisim does? I hope so. So let me just call this lab. Well, that didn't work. Why didn't that work? How can you record video? You should be able to record just using a screen scraper. I don't know what the best way to do that is, does... Yeah, I don't know what the best way to do that is in... I thought there was a way to do it in Windows easily enough. I thought the... yeah, at least for Windows 10, doesn't what used to be... Windows Shift and F keys, apparently. Let me take a note and I will find out and post more information in the lab. So recording on the screen under Windows.
On my computer, if you press Window G, it'll have a capture option.
And it allows you to capture as a screen scrape, a video scrape, yeah?
Yes.
Okay. Yeah, I thought it was inbuilt in Windows these days, but depending on what version of Windows you have. Under macOS, you just use QuickTime. That shows it up. WinKey, sorry. What version of Windows are you running, Justin? Let me know, and I'll figure out how to. Windows 10. What does show all captures do? Ah, maybe the game bar needs to be enabled. Anyway, no comment. Sorry, I think the laugh was enough comment. For some reason, that image is not coming across. Let me see if I can find when I took it before. And I think that's the one. There we go. That's a bit better. Let's just make it a bit bigger. Right, so we want to, the first thing we've got to do for this lab is design a circuit, right? So a way to do that, or we could, so we've got two inputs, A and B, and we've got two outputs, C and S. So we need, well, one way to do it would be to do a 2x2 Carnot map, but that seems a little too simple, right? So I think C is pretty easy to generate, right? So C is only a 1 when both A and B are a 1, right? So C is just AB. And then S, and my coffee's arrived. Let me just see if I can. Ah, it's nice to have delivery service. Okay. Right, so, and then S is, well, one way to do it would be to say that's A, B bar, or A bar, B, right? And if you remember before, we had something similar. So that is really just A exclusive OR B. Right, so the circuit we want is something like this. AB and there's our C, and here's our exclusive OR device, and that's our S, let me just do that. Okay, so that's effectively the circuit we want to do in multisim. So I suggest if you have access to multisim that you fire up multisim and try and put these things in there. I've forgotten the standard AND gates. So 741, let me just kill that screen and move that one back here. So what's the AND gate?
LS
08, is it? Could be. I have forgotten. Yeah, quad 2 input AND gate. Okay, so that's good. So this one is a 7408, and then I've forgotten what the exclusive is. A 32, is that right? No, that's an OR gate.
Could you go over how to use multisim or how to find stuff in multisim again? It's been a while.
Yeah, sure. Let me just get the number for the exclusive OR gate, and then I'll go back to the oh, it's 86. Okay, 7486. Right, oops. Let's go back to drawing. So that's a 7486.
Is that the one with the LS?
Yeah. Most of the newer versions of the 7.4 series are LS. I'm just used to. When I started, LS was brand new. Does anybody know what LS stands for? Okay, LS. Is low power, and I probably spell it incorrectly, Schottky, right? L and S.
Does it matter with if it's the D or the N?
Shouldn't matter, no. So as I said, when we went from RTL logic to TTL logic, one of the constraints, or one of the reasons we did that, was because of power. And again, there was a slight modification using a Schottky diode instead of, or a Schottky transistors instead of the standard transistors. And again, the aim was to reduce the power consumption of the logic gates. So that's why we moved to LS. And then there's various other modifiers, D and F and various other things. It's usually LS. H, I think, might be there as well. I think H is a... yeah, maybe I'm wrong. I thought H might be CMOS, but I could be wrong. Anyway, okay, somebody asked about how do we do this in multisim. So let's do that. Don't know if I can make that size bigger. So let's just call this, can I rename it? I don't know whether I can rename it. Let's save as, and I'm just going to make sure I save this on my OneDrive, and I'm going to do it under the work directory that I had before, and I might make a new folder called lab 2. Okay, and we'll call it lab 2, well, CET466 lab 2. Okay, somebody's typing. I don't know. That's okay. It just sounds quite loud to me. It's all right. Let's just make this full screen. Might make everything a little easier, and then see if we can zoom in. Make it a bit bigger. Ooh, it's a bit too much, I think. Yes, let's zoom to the sheet. That's better. There we go. Right, so now what we need to do is one of these little dots is place TTL, right? And then what you do is you select a component, and we want, what did we say it was? It was an 08, is that right? Right, there's a J and there's an N. They don't, I can't see a lot of difference. They're both quad 2 input. The package.
I thought we're using the LS one.
Sorry?
Isn't it 74 LS08?
It could be 08. For this example, there we go. There's a D, there's a J, and there's an N. And it looks like the only difference is the packaging. And I don't have a clear idea of what the... Ooh, that one's... what the difference between the packaging is. I suspect it's the difference between through-hole components and surface mount components. Because we're not going to actually be designing a printed circuit board, it really doesn't matter much, provided it does give us an AND gate. I'm going to go with the N, and we just want A, and I don't need anything else, so I'm just going to cancel. I just need the one gate, and then the other one, what was it? Was it an 86, right? And again, we've got a D and an N. I'm going to go with the N again. Probably best to use the same packaging on all devices. And I'm going to choose A again. Right, and then cancel. Now, what we need next is we need to have inputs. And there's a couple of ways we could do inputs. One way, because there's two inputs and we want to exercise all possible values of the input, one way would be to have a 2-bit counter and have the counter go 0001 1011 00101 1011, etc. Continually. That might be a little, considering we've only got 2 gates for the circuit we want to exercise, that's probably a little bit of overkill, right? So let's not do that. I'm just going to connect up some switches to form our inputs and some lights to show our outputs. And to tell you the truth, I have forgotten how to search for lights. So let's
it's in the indicator group.
It's in the indicator group, is it? So we go in here and indicators, there we go. And I think it's
under probes.
Under probe, right? There's a blue probe. Let's make the this is CCSU, so let's go with the blue probe, right? So we can have that there, and I need two. I need one for each of them, right? And then I should just be able to connect that up there and that up there, right? And let's just go back to our right, so the output of the AND gate was C and the output of the exclusive OR gate was S. So instead of X1, I'm going to call that C. And the reason it's called C is because that's the carry. Right, that's the carry bit. I can't contain delimiters, so I'm just going to call it carry. Right, and this one, that's called S because that's the sum. Okay. And what else do I need to do? I need to give some inputs. So let's go back and place another component. I need power supply. Do I have a power supply? I've forgotten the... I need a voltage source. I probably...
You have to change the group again, and it'll be sources.
It'll be which power? Is that right?
Sources.
Sources.
Or you can go to all groups and you can type in VCC.
Okay, we can do that. Thank you very much. I haven't used... there we go, VCC. Right, so there's our supply voltage. Hidden power pins are using placing this global conformer connection to these pins. You want to continue? Yes, I do. So there's our VCC and it's labeled at 5 volts. That's good. I also want a ground. Right, so I'm going to put that on. And we'll put that down here. Let's just make sure it sort of aligns with that. I also need a switch.
That one is in basics.
It's in basics.
Yes.
Okay, so that's
And then if you want the name, it's like DSWPK.
DS WPK. That's a switch package, right? I suppose we could use a switch package. That'll do.
If not, you can also look at the switch category in the family side.
Mm-hmm.
I think what he might be looking for is the DIP SW.
DIP
Yeah.
and SW1, SW2. Yeah, SW1 might be okay too. Any of these would work, right? So I'm going to put that one there, and I'm going to put that one there. Let's use that one. Let's use those two. They're just a bit easier to see than the tiny little dip switches. Okay. So now we have, in fact, let's just, how do I change the key? So I'm going to make that one key B. Okay, so this one is A. The label, instead of being S2, is A. And this one, instead of the label being S3, is B. Okay, and if I type A, it toggles the... You can see it toggles whether the switch is open or closed. And if I type B, it toggles the other one whether it's open or closed. Now I just wonder whether I can rotate them, because I prefer them rotated. Maybe they'd be better the other way around. But anyway, that'll do. And I'm just going to move that guy down here. Now, what we want is to be able to set A and B separately to be either 1 or 0. And the usual way to do that is, right, we could have put a 2-position switch here and have one of the 2 positions going straight to VCC and the other one going to ground. That gets a bit ugly. So what I prefer to do is to use either a pull-up resistor or a pull-down resistor. Does anybody know what that means? And let's go with bingo again. Quentin, do you know what a pull-up resistor or a pull-down resistor does?
I vaguely remember, I think it's like, let's just say the output's like 1. It would go like straight to ground or something, or vice versa, something along the lines like that.
Yeah.
Where you're pulling up, when the input's maybe 0, it goes to like the pull-up resistor. I can't remember.
That's
like something like that.
Yeah, that's pretty close, right? So let me just move. Eek. I wanted to move the switch rather than. So I want to put these 2 switches so that they're roughly at the same level, right? What you do, and I'm going to use a pull-up resistor, right? And a pull-up resistor, let me just, can I get a resistor like that? That's not a resistor. Oh, let's just go, ooh, that's actually got a picture of one. I don't know, will that one do? Yeah, let's put that one in there. And let's just rotate it like that. Right, and I'm going to put that one there, and then I'm just going to copy it. Control C, Control V, there. And then I'm going to connect that there, maybe. And then connect that one there. Right, and then I'm going to connect the resistors up, and then I'm going to connect everything up to ground. Okay, now what this does is, let's just open the switches, right? What this does is the voltage here is now 5 volts. The reason it's 5 volts is because even if I connect it to one of these inputs on logic devices are very high impedance. They're very high impedance, so that means very little current will flow through them, even when there's a voltage. If there's very little current flowing through here, then the difference between the voltage on this side, which is VCC or 5 volts, and the voltage on this side is negligible, right? So the voltage here is 5 volts with this key open. The voltage here is 5 volts with this key open. If, on the other hand, I close them, I've got the wrong, yeah, so now on this side and this side, now I've got a direct line to ground. So now my voltage on this side is ground because it's just connected to ground via a wire, and same here, right? So this sort of way of doing things is called a pull-up resistor, right? When there's nothing else happening on this side, the voltage at here and here gets pulled up to whatever the voltage supply is. Okay? So what we can do maybe is connect that one up there, maybe. A bit of a loop, connect that one up there. Connect that one there. And that one there. Okay, and that should be everything. So let's just run the circuit. I don't know whether it's going to work. I don't know whether I need to do something else. Okay, so the input to our circuit, A and B, both keys are open. That means the pull-up resistors are pulling up A to logic 1 or 5 volts or VCC. They're pulling up logic the B to VCC as well. So the two inputs to our circuit are 1 and 1 now. And remember, if we go back to our truth table, if the inputs are 1 and 1, then the carry needs to be 1 and the sum needs to be 0. And you can see on our lights on the output, the carry is 1 and the sum is 0 because it's not lit up. If I close both of them, right, now both inputs are 0, so both the carry and the sum are 0. If I open up A, then the sum is, A is 1 and B is 0. So the sum is 1 and the carry is 0. If I swap those over, same thing happens. The sum is 1 and the carry is 0. Okay, so basically all I want you to do for this lab is to put together something like that and do a screen scrape. If you can't find a screen scrape, take 4 screenshots, right? This is one screenshot. There's another screenshot. There's another screenshot. And I don't know whether that's the other screenshot, right? So 1, 2, 3, 4. Just to show that you've exercised all possible inputs to the circuit and yeah, that it works correctly. Okay, let me just see if I can transfer my coffee. I might just turn my video off while I do that. Oh, my video's been off all the time. That's all right. I forgot to turn it back on again. Hello, I'm still here. Let me just do that. Does anybody have any questions on what I just went through? Does that all seem okay? Are we dismissed? I don't usually do a formal dismissal. If you are happy with everything so far, then look, I have taken attendance, like I said, with the bot does roll call. I don't usually put any. Let me just turn that back on again. I usually don't turn. In fact, let me do it that way. I usually don't do anything based on attendance, right? If you can get high grades without having, without coming to class, good luck. That's really good. Most people can't. And it's okay if you need to leave early. I like knowing, that you are, but it's okay to leave early. It's professional to communicate that you're doing that, right? you don't just slide off into the sunset. But you know, it's there's no what's the word, penalty for not turning up. Okay, let me just check the what's happening on. Okay, so Ray and Wei have already submitted lab 2. Thank you. That was quick. Okay, Dave, that's all right. Let me just check. I'll see whether you were. Like I said, I don't use it. My main reason for using it is let me just run the. Yes, please. If you want to do the screenshot version, just this lab 2 is due Saturday next week, right? I always give a. I'm going to spend time online with each lab, but it's not going to be due that day. It's going to be due a week after we do the lab in class. Okay? You're welcome. Okay, I'm just going to save that, and unless anybody's got any questions, I'll leave the lab there. Actually, that's a really good question. Let me, Anthony, it's a really good question. Let me answer it in a very long-winded way, but maybe it'll be useful. Okay. I have a, and I'll share this if I can figure out where it got to. There it is. Right, so I have a few things that I look for, and what I'd like, not for this lab, but starting for the next lab, is to start doing things in a more professional way. And this is something I wrote up a while ago about what I look for in a lab report. It doesn't have to be a lab report, but right. The first thing I look for is an abstract, and it doesn't have to be a very long abstract. In fact, in most of the ones we're going to be doing, the abstract and the introduction are probably just the same thing, and they're one sentence, right? And what the abstract and the introduction together should do is they should say, why should the reader continue reading, right? If I don't have an abstract or I don't have an introduction, then if it's just pictures, then that's not telling me much. Right? So from next time, I want you to think about having these sections. And it may only be one sentence per section. Most of the labs we're doing in this course are relatively small. The project at the end is bigger, and that will need more of what we're talking about here, but most of them are relatively small. Right, so the problem statement, right? It should answer, what is the background information that I need to understand the report, and what happened that made this report? Why did you do this report? Then maybe there's some equipment or labs or procedures, right? And the reason you do this is because you want to be somebody else to be able to reproduce what you did. Then there's the results. and the results may be numerical, in which case you probably want to draw a graph, right? And I actually should update this. I've got another. When I used to mark lab reports, and the lab report had a graph with no label on each axis. I would handwrite as I was grading them. One axis would always be litres of blue cheese, and the x-axis, it wasn't days. I actually used to use furlongs per fortnight, right? So unless you don't know, a furlong is a distance of measure. It's usually used in horse races primarily these days. And a fortnight isn't used so much in the US, but a fortnight in most of the rest of the English-speaking world is a 2-week period, right? So it's a furlongs per fortnight is a measure of speed. It's just a very bizarre measure of speed. And then there should be a discussion. What went right? What went wrong? Was the experiment a success? What could you do better? And then a conclusion. And then just a quick word on spelling, grammar, formatting. I don't tend to be too critical because my English was learnt in Australia, which is not American English. It's still English, but there's lots of idioms and different things. The usual example I give is if you're in Australia and somebody asks, "How are you?" and you're okay, I would just say I'm fine, and that would just be there's nothing too good, nothing too bad. It's just normal. And I used to live in Ireland, and if I got asked the same question, how are things, and I said I'm fine, the immediate response from people was, "What's wrong?" Right? Whereas in Ireland, the everything's normal response to "how are you" is, "Oh, I'm grand," right? And there's similar things with between Australian, Irish, and American English. So I don't get too hung up. Where I do get hung up is if I can't understand it at all and it's impacting communication, right? So then I will give more feedback on whether it's grammar or spelling or organisation or what have you. Try and make sure if most of the reports in this subject don't use references, right? The only reference would be the lab sheet, which is there's no point in referencing it. But if maybe for your final report there are references, and I highly recommend you use the IEEE citation style, and there's a link to it on the LibGuides site. Sorry, Anthony, that's a really, really long-winded answer, and it didn't explicitly answer your question. To explicitly answer your question, yes, when you have diagrams like this, I believe there is a title block. There it is. I don't know. Does that one work? Right, and this one's probably a bit big, but I recommend using a title block and filling in parts of the title block. Okay? So, yeah, I normally with these sorts, particularly if you're just doing screenshots, that way at least it's clear who's done it. And so yeah, so I do recommend using a title block. Oh, okay. And I'm not too worried about it for this one. I just want to start getting into the habit of being a little bit pickier as we move through the course. So by the end of this semester, I am going to be quite picky about what is and isn't in a report or on a diagram. But for now, it's the second week of semester, so we're all still getting up and running. Okay, so I try and crank things up or down, depending on which way you look at it, as we move through the semester. Okay, I'll save that. Okay. As far as I'm concerned, I am done with today's lecture. I'm happy to stay on for the next half hour or so and answer any questions about labs or what have you.
Professor.
Yeah? What's up?
I'm trying to find the switches in multi-sim.
Okay.
And I can't locate them. Where are they at?
Let me fire up multi-sim again. Right, and let's just... So master database, all groups. What did we call it? It was a...
The switches.
Yeah, the switches. I've forgotten what we called it. Let me open up... It's DIP SW1. Right?
What's it called?
DIP SW1.
DIP.
And we need to select all groups.
Should be DIP SW1.
Yep, so you've got to select all groups and all families. Oh, there we go. Basic switch DIP. Thanks, Javier.
Okay, cool. Thank you.
You're welcome.
What is quartus for?
What is quarters for? I haven't... Oh, can you maybe mute hearing myself talk? Zach, I'm just going to see if I can mute you. There we go, that's better. Okay, so what quarter... We haven't got there yet, and I really haven't talked about the prime reason for this course yet, right? Quartus is if I were a software engineer, Quartus is what I would call an IDE, an integrated development environment for turning code, either Verilog or VHDL, we're going to use VHDL in this course, is for turning code into something that will implement logic circuits, right? So let's just... this is probably a bad example to use, but I'll use a Verilog example. This is the code that we compiled before, right? And this is quite a complicated module. It's got a clock input, it's got a switch, it's got RGB horizontal sync, vertical sync, LEDs, beep, digit and number. So the switch and the clock are inputs, and then everything else is an output. And there are 4 switches labeled 0 through 3. And then we've got some registers or variables if you like. And then we've got some logic that connects everything up. And what Quartus lets us do is this will compile this down into something that will run on this board. All right? So this code, when you run it on this board, and I don't know whether I can easily, let me see if I can do that. Maybe. I need to power it up. So let me just, sorry, I just got to connect up a USB cable to power it up.
In my microcomputers class, we used a program called like Embedded Workbench for our launch pads. I think it's similar, right? Where we're using Quartus to compile code into the device.
Exactly, right? And let me just see. I don't know whether I've actually blown this one. It's not going the way I oh, I probably didn't blow it. Yeah, anyway, no, it's not going to work. But basically, when I have that board connected up to my Windows PC, and it's a bit hard to drag everything over, so I won't do that. But yeah, this code compiles down to run on the board, and this code combined with the pin planner, right? The pin planner lets us connect the variables that I named in my code to specific output pins on the device, so that I can connect up the LEDs to where the LEDs go, the switches to inputs to where the switches are coming from, etc.
Oh, okay.
Okay, does that make sense?
Yes.
Yeah, and we'll be going into more detail with that shortly.
I had a quick question, Professor.
Yeah.
It's about the grade for Lab 1. I got an 80 out of 100, and I didn't really get a comment on it, so I don't know if that was
Right.
an error or maybe even was something.
Right. So I thought I said during before a little bit before what you what I ooh, that's no good. I thought I'd assigned a rubric to that, but I obviously haven't. Sorry about that. I thought it was obvious from the rubric, but it looks like I didn't actually put a rubric. So what I said in the class earlier is what I'm looking for in the Quartus screenshot is the fact that you've actually compiled the example code that I made available, right?
Oh, okay. Okay.
And I don't think you had all green ticks in this tasks window in your screenshot.
Yeah, I don't believe I did.
Okay, so if you can upload another copy with the green ticks, then that'll get the extra 20%.
Okay, thank you.
You're welcome. Sorry about that. I thought I'd made that clear in the rubric, but it looks like I didn't assign the rubric. I made the rubric, but I didn't assign it to the lab. Apologies for that.
Have a nice day, Professor.
Okay, thank you. I've got a couple of people in private chat, so I'll just See if I can
See you
help
next
them.
week. Bye.
Yep. Bye bye. Thanks all. I'll go back to small me.
I will get you a new document of Cortus as soon as I can.
Yeah, no
Have a good
worries.
one.
Yeah, thank you. Bye bye. Okay, I'm going to stop sharing my screen.